Okay, that's what we needed. Is Konstantin Batygin, who's well known to most of us, maybe even all of us, is going to talk about Planet Nine.
All right, thanks very much, Charles. Sorry?
Which spelling, the German or?
Oh, you're gonna find out. Okay, you're gonna find out. Okay. Well, listen. It's been so much fun learning about all the stuff about dark matter. In this talk, I'm going to try and talk about dark matter that we'll hopefully see at some point. And also I should caution that last night was so much fun that I feel like I'm losing my voice. If I just go silent, okay, halfway through the talk, it's not because I'm nervous. Just try to interpolate between the slide and then figure it out. And the third thing I'll say is last night, Vadim and Olga, Ilsa, and Smadar have all challenged me to not only give my talk fully in Mathematica, but to create the slides live in Mathematica. Okay, so we're gonna do that right now. Okay, I'm good at this. I'm good at Mathematica. Okay, so I'm gonna import Wolfram, hypermind, consciousness graph, and it's just like, oh, it worked. It worked. Okay. Thank you. Any questions? Any questions? Q&A. Okay. All right. So let's get serious. All right. In parallel with like the exoplanet revolution that has unfolded over the last 25 years, right? We've had a parallel revolution in the outer solar system with the detection of the Kuiper belt and the characterization of its large-scale structure. So for scale, of course, this is the outer solar system: Jupiter, Saturn, Uranus, Neptune. My house is right there. Okay, this is the orbit of Pluto. And in a second, we'll see all of the kind of well-characterized orbits of the classical Kuiper belt and the resonant Kuiper belt as of a few years ago. So you can see that the Kuiper belt is in fact not a belt. It is a donut. It was not really predicted by Kuiper. It was in fact quantitatively predicted by Martin Duncan. This is a Dunkin' Donut, okay? Why is the Dunkin' Donut there? Okay, it's like, I love making that joke here because everywhere else people just are quiet and they just don't laugh. Okay, so why is the Dunkin' Donut there? Okay, well, the Dunkin' Donut didn't start out, okay? It started out instead, okay, between sort of 15 and 30 AU when the solar system formed in a more compact configuration. And during the first 100 or so million years of the solar system's dynamical evolution, the giant planets migrated through this disk of 20 or so Earth masses of material, underwent a transient period of dynamical instability, and then recircularized where we see them today. This is collectively known as the Nice model. There are lots of variants of the Nice model, but they all kind of tell the same story. And for the purposes of what we're doing here, it's important to understand that the Kuiper belt we observe today is the mere remainder, right? That last 0.1% or so of the material that was initially there and then sort of has been trapped, right, beyond Neptune's orbit. Yeah, so we'll see all the orbits appear momentarily. Okay, so over the last, I would say, really 10 years, this story, okay, has been worked out in really, really remarkable amount of detail to the point where it's now possible to read off what the eccentricity and inclination of Neptune must have been as it was traversing 28 AU, right? It's that level of detail that you can read off from the structure of the resonant Kuiper belt, etc. Now, something that cannot be understood within the context of the Nice model, however, is the distant portion of the so-called scattered disk, the most distant orbits that we know of in the solar system. And this has been an ongoing saga, but the main idea is something you can just see in this visualization, right? If you look at the most distant things that take 10,000 years to go around the sun once, you can see that they're all tilted in a common plane, which is inclined with respect to the ecliptic by about 20 degrees, and they're all kind of pointing in the same direction. Okay? So that breaking of symmetry, both axial and polar, is not something that the NICE model, really any model will produce, it requires an external perturbation. So the data set has evolved quite a bit since we wrote the first, Planet 9 paper with Mike back in 2016. So this is from a paper with Morby from 2017. This is from a paper together with Fred and Juliet from 2019. As you can see, also my ability to make a graph is also increasing in time, okay? And something that, and then as we kind of dial the clock forward, this is sort of what the data set looks like today. So I would invite you to notice that not all distant Kuiper Belt objects are created, well, they're all created equal, but some are more equal than others, okay? In particular, the ones that are labeled here in purple, okay, are the ones that are dynamically stable. They have perihelia, which are detached away from the orbit of Neptune. So they are, if you put them into an in-body simulation and let them go, nothing will happen. I mean, their orbits will slowly precess on the time scale of 500 million years or so due to just gravity of the planets, okay? And that's it. Conversely, the green orbits, right, are the unstable ones. They're the scattering objects. Their perihelia are jammed into the orbit of Neptune, and you can think of them as being on their way out of the solar system. If you let them go, in hundreds of millions of years, they will escape. Okay, and again, in sort of a eye by eye way, you can do more sophisticated things, but you don't really need to. You can kind of tell that only the stable orbits cluster, right? The purple ones are pointing this way, and that projection over there of the angular momentum vectors sort of shows the same thing. It's the stable perihelion detached subset of the distant orbits that shows any sign of exterior perturbation because, right, after all, once you get jammed into the orbit of Neptune, you're completely dominated by Neptune scattering. Okay, so why do we see this? Well, a kind of temptation always to explain all things solar system is to say, well, something bad happened to the solar system when it was forming 4.5 billion years ago, and that's what we see. Okay, to kind of make a Big Bang version of an explanation, you outsource all the interesting stuff to the formation. And people have talked about the idea of, okay, the solar system formed in a cluster. Could you have a passing star, right, pass by within a few hundred AU? You absolutely can. In fact, it's expected, right, and create this pattern, and now we're seeing the relic. Is that viable? And the answer is no. Okay? And the reason it's not viable is that all of these orbits have different semi-major axes. If you just leave this system as is and allow it to evolve over the lifetime of the solar system, in a few 100 million years, they will all precess out of alignment. So if you kind of believe that what the data set is showing to you is actually real, right? If you kind of take the data at face value, then something has to keep the data, keep the orbits confined. Okay, what can that be? It can be anything. It can be a 5 Earth mass primordial black hole, or a 5 Earth mass burrito, 5 Earth mass planet. All of these things will work just as well, as long as it's about 5 Earth masses, as long as the orbital period is about 10, 20,000 years, and as long as the orbit that is perturbing the distant solar system is both out of the plane to tilt the Laplace plane of the outer solar system, and appreciably eccentric to break the axial symmetry, right? And this is one simulation where you have Uranus and Neptune, the orbit of the perturber, in this case, Planet 9, here in this big pink ellipse, as well as an initially axisymmetric disk of long period orbits, right, that evolve in a self-consistent manner over the lifetime of the solar system. Now, you can tell that the evolution is wildly chaotic, okay, and it takes a while for the pattern that we see to get carved out. It's going to get carved out 10 more seconds, okay? We just have to wait, okay? We just wait, okay? Okay, now it's there. Okay, you guys see this too, right? Okay. So what's going on? How come the orbits that are preferentially surviving are the ones that are anti-aligned with respect to Planet 9? What's happening? Well, the physical explanation is that when these distant things go through their precession cycle and they align with the orbit of Planet 9, their eccentricity goes through a peak. And when it goes through a peak, their perihelia get jammed into the orbit of Neptune, and Neptune ejects them. Okay? So in this story, you naturally generate a strong correlation between perihelion detachment and the degree of confinement. Okay? That makes sense? All right. Okay. One more thing that I will say as we go into the ecliptic plane is very often, in fact, quite robustly, you will see objects like this, okay? In like every single simulation, you generate a distribution of highly inclined objects. Even if you fail to reproduce everything else, you always puff up the inclination dispersion of the outer solar system way more than what you could plausibly expect in a just regular planet formation. So we're going to come back to the highly inclined population in a little bit. Okay. And here, okay, what I'd like to do next, well, I wasn't going to talk about this slide, but okay. You can write down a Hamiltonian. You can just orbit average, as long as you keep yourself to the plane. All of what we saw on the previous slide, you can kind of understand within an integrable framework, okay? I don't want to dwell too much on that because there's a sharper question, which is, okay, I said, right, if you believe what you see, then all of this makes sense. What if there's a deep state conspiracy, okay? And what you see is a consequence of observational bias, okay? And this is a notion that in fact has been pointed out kind of multiple times throughout the last 8 years or so, right? First, with respect to weather patterns, maybe if there's weather patterns and that's why we only see orbits on one side, or maybe because surveys tend to avoid the galactic plane, right? Maybe we're seeing that. Turns out these things come to perihelion right next to the galactic plane. So it's not that. So this notion of bias has been kind of a recurring theme in the Planet 9 story. But in 2021, it kind of reached a peak when it kind of went viral on Twitter.com. Okay, because the paper came out, you can see the tweet, right? It's like the most comprehensive study ever that examines the original clustering argument, right? Just like doesn't exist. Joanna Drozdowska says, don't let the Avi Loeb drama overshadow the fact that whole Planet 9 evidence died this week. We're titled Planet 9. Okay, this joke just kills every time. Okay, right? Planet 9 postdoctoral researcher says the woke are getting more woke. I don't know why that's relevant, but it's also there. Okay, right? Planet 9 is dead. All right. And that video, by the way, was a documentary of some of the beatings that the Planet 9 hypothesis has experienced. Okay. What's actually interesting is if you read the paper, this says this work also does not analyze whether some form of clustering could be consistent with the 14th unit. Okay. So this is an interesting exercise in how the information compression of Twitter.com operates. But I should say, all of this, okay, is not crazy, okay? It is true, ultimately, that there are very strong biases associated with the detections of objects in the outer solar system, right? They're brightest when they come to perihelion. So if you have a survey that only looked over there, then you will find, naturally, a bunch of orbits that are long period, that are clustered with perihelia over there. So how do you go about kind of calculating the false alarm probability? Well, there are two ways. One is to do survey simulation, right? And what has been shown is that at the individual survey level, there's not really much that could be said, right? There's not much that could be ruled out, right? You can't demonstrate that the orbits are clustered. You can't demonstrate that they're not clustered. a distinct approach, which I like to refer to as the kind of observability mapping, is to in fact forget about who discovered what, and to just take all of the data of the outer solar system and project it on the sky and say, okay, let's say, I don't know, Avi was looking for a meteor, okay, but instead he discovered a Kuiper Belt object and he reported it to Madden, but didn't sign his name. Okay, I don't know that Avi did it, I don't know where he looked. The fact that he looked over there and found an object of, say, magnitude 19, to me, once I read the MPC, I know that somebody looked over there and was able to discover an object of some magnitude or bright. Okay, so you can, if you kind of take that approach, not survey simulation, but observability mapping, then you can kind of have a pretty good idea of where people have looked on the night sky and to what depth, okay, at least the lower limits. Okay, and then you can ask the question of, given that distribution of discoveries, what are the chances that you will be seeing this alignment by coincidence? And it's about 0.2%. Okay, so it's not like a 25 sigma. Like if you're a particle physicist, you might be pretty unsatisfied. It is what it is. There's a 2.2% chance that those that alignment is just completely not there. I should mention at this point, it's actually less than that because DES data has shown that the tilting of the plane alone is about 2.5 sigma, but this is still an okay order of magnitude to keep in mind, okay? So I want to be honest about that, okay? And with that said, I want to return here and talk about, that highly inclined object that you've been keeping in mind. Okay, so as I mentioned, the generation of high inclinations in the outer solar system is not something that planet formation can provide you with. It's not actually something that Neptune scattering can provide you with either, because of conservation of Tisserand parameter. Okay, so if a population of distant, highly inclined objects really is out there, it would be pretty cool. And it is in fact out there. It was discovered by the WISE mission. And we were hoping this would be a great prediction, but in fact it was a retrodiction because they had been already discovered. We just didn't know. They didn't know we kind of made a big deal out of the fact that the really long period centaurs are all tilted onto sometimes retrograde orbits. So, okay. Then, okay. And we try to attribute this to Kozai, okay? We try to be like, go into the same direction as Madar, and we couldn't, okay? Because the way that it's generated is not by Kozai. They're generated by distinct secular octopole level harmonic. Okay, so they're there, okay. Now, sometime later, okay, the Pan-STARRS survey discovered an object like this, which the paper termed Niku, which in Chinese is supposed to mean rebellious, and in Japanese it means meat. Right? And I don't speak Chinese, I don't speak Japanese. Okay, so the meat, okay, orbits the solar system in this, polar orbit, okay, part immediately outside of Neptune, and it's not long period. So everything I said up till now is clearly not applicable to it, okay? Because it's in the wrong part of the solar system. Like Planet 9 driven dynamics, if it's there, don't do anything immediately outside of Neptune. So what gives? Well, to understand the origin of this population of bodies, what you need to do is not delete objects when they veer inside of Neptune. So in the previous simulation that I was showing you, when objects would make their way with perihelion sufficiently close interior to Neptune, we would just remove them from the picture so that you could see the emergence of the clustering among the stable objects. But if you examine what the things that cross Neptune's orbit are doing, and highly inclined things that are doing their chaotic, flipping dance, okay? A fraction of them, of course, get ejected out of the solar system, but a distinct fraction, right, diffuses in, okay? And in fact, we reproduce a population of these types of tightly bound, okay, polar orbits, okay? And this is nature's way of saying, if you liked it, then you should have put a ring on it, okay? Now, this is what the data looks like now. The data are the blue dots. The background here is where Planet 9 models emplace the objects. I think each one of these plots individually is not that staggering. I think their union is considerably more meaningful, right? And for reference here, what we're plotting on the x-axis is the perihelion distance versus inclination. And here it's center major axis versus inclination. Now, importantly, I should mention that there does exist a counter idea to how to produce this population of bodies. And that is to basically tilt them by galactic tide when they're in the Oort cloud and then scatter them in, okay? But Nate Cave and collaborators have shown that that process would generate flux that's a factor of many, many less than what we observe, okay? Conversely, the kind of canonical Planet 9 will give you the flux that you need. Okay, so for a while, these four lines of evidence, right, the fact that the distant stable orbits are clustered together, the fact that their angular momenta are tilted together, the fact that there are these long period, highly inclined objects, and the fact that there's a population of retrograde polar centaurs, that kind of was the evidence that we had for Planet 9 being spelled in a particular way, okay? But recently, in fact, a year ago, we stumbled onto a new thing, okay? And this new thing can be summarized as a very boring statement, okay? So up until now, I've asked you, right, for the original kind of clustered population to ignore the highly eccentric, things that hug the orbit of Neptune, because those things are dominated by Neptune, they don't matter, okay? But let's now go to the other extreme and say, what about the things that are absolutely unstable, the most unstable population of TNOs? The most unstable population of TNOs are the ones that are in the plane of the solar system and cross the orbit of Neptune. If you integrate them, they're all gone in 100 million years. So if they're there, okay, they require a production mechanism. And if Planet 9 is there, by virtue of modulating the eccentricities of distant orbits up and down, it would provide a steady flux of long period Neptune crossing objects. And here are some simulation results that kind of show you that perihelion distance is on the y-axis on this plot. You can see them all dip below the Neptune orbit at the end of the simulation. So, okay, given that that's true, okay, let's compare the scenarios. Right? Scenario 1 is one where we include Planet 9. Scenario 2 is one where we don't. Okay, that's this one. Okay, I know. So, interestingly, as I mentioned, even if you don't have it, you can produce them by the galactic tide mechanism, but the distribution of perihelion distances that you get is vastly different. In the galactic tide picture, it has a hard time removing the orbits from the perihelion equal third, okay? So the orbits kind of remain attached to it. And so the perihelion distribution is very, very peaky. Conversely, in the Planet 9 case, you get a pretty flat distribution between 15 and 30, okay? So what does the data look like? Well, it turns out there's now 17 of these objects detected, thanks in large part actually to pan-stars and DES and such. And I'm running out of time, so I'm going to skip the debiasing thing, but the point is after you go through the process of biasing the simulations prefer the Planet 9 case over the Planet 9-3 case. The data prefers the Planet 9 case at a 5 sigma level. So this is kind of the most boring population of TNOs that you can have, okay? They're in the plane of the solar system. They're across Neptune's orbit. There's nothing exotic about them. But interestingly, their perihelion distribution provides what I would say is the most strong evidence for the existence of Planet 9. Okay, all of this stuff will be confirmed by, confirmed and tested by LSST, which is great. Unlike many pictures that we saw today, this is not a ChatGPT generated picture. This is actually what it looks like. You can tell because there's some kind of an encampment going on over there. And GPT-4 training set ends in 21. And that is, now Avi has asked me to play guitar yesterday. That's roughly what my solos sound like, okay, except for a little faster. But I will say that since we couldn't secure a guitar, you're welcome. I will say that my friend Eduardo Marturet, who is the conductor of the Miami Symphony, learned about this Planet 9 business, got excited, wrote this amazing 19-minute symphony, which doesn't have a time signature. You just play it, like you feel it, okay? And we played it in Miami a couple times, and then during the pandemic, we recorded it, okay? And then we used 28th century technology to call the International Space Station. We talked to this guy, Soichi Noguchi, and we played it for him. We actually used Microsoft Teams, okay? It was not advanced at all. And he politely said that he liked it. But the YouTube comment section has a different opinion, okay? For example, David Gersman says that this is dripping with the usual self-importance and arrogance one can always expect from composers and musicians. But other than that, it was okay. Smokey McPot says this is bizarre science, Planet 9 meets pseudoscience face veils. Okay, so Smokey McPot is unvaxxed, unmasked, unafraid. Okay, I will stop here and take any questions. Thank you.
Do you have any questions? Okay, Avi.
So in the P9 free case, this was not the most realistic case because every now and then a star passes by. Now, at any given time, there is a star roughly at the edge of the Oort cloud, but if you go over 1 million years or 1 billion years, stars will come closer and closer. And first of all, that would pose a risk, tidal disruption of Planet 9, but also it would change your prediction for perihelion distances. Did you look into adding passing stars?
Actually, it wouldn't because we added them and did it all self-consistently.
Ah, okay. But Planet 9 survived.
Yeah. So because its semi-major axis is about 500. The chances of a passing star in the field disturbing it are like 10 to the minus 6.
Over which time?
Over 4.5 billion years. Yeah, in the cluster, right? It's high, and that's in fact how you produce it.
I have a question. So you quote the number 5 Earth mass. How much room do you have to play in that number? Like, do you have an upper bound and lower bound?
Great question. So it's correlated with the orbit that you, that number basically comes from the degree of alignment. There isn't a factor of 2, okay? 2.5 is out, okay? 10 is kind of also out. And I also forgot to say that I asked Wolfram Alpha to give me parameters for Planet 9, and it said it's at 2.5 AU. That's why we haven't found it. We've been looking at 500. It's been at 2.5 AU all along. Okay. Yeah, that's right. I got to upgrade to Pro.
Okay, so we'll take one more question.
Thank you. Excellent talk. I think of all the lines of evidence that the most recent paper you put out is at least to me by far the strongest. And it's kind of funny how these quote unquote, I just call them boring objects, like they're not supposed to be there, and that's pretty convincing. But here's a question: one, can you rule out more than one planet? And two, so I think Brett Landman and company have been doing these simulations with, I think, multiple Earths embedded in the outer TNO belt. And then the second, what would it take to falsify Planet 9? Is there something in Rubin, let's say in the next 3 years, that you just expect to be there? If it's not there, we go back to the drawing board?
Yeah, okay. I appreciate appreciate all that. Let me answer with the first one first, which is, could there be multiple? In principle, yes. There's no need in the model to have more than a single body. So for now, no. Eventually you run out of real estate because orbits become unstable in the cluster phase. So you can't keep parking more and more planets out to thousands of AU, because the process that traps them in those orbits also removes them. Okay, but so it's not impossible. It's possible, but there's no evidence for it for now. Number two, with regards to rogue planets, a la what Huang and Gladman have been doing, I think it is a implausible scenario because they require the kind of 2 Earth mass object to hang around in the outer solar system for a few 100 million years and then get removed. Okay, you can remove it by cluster interaction, but the solar system did not form in an open cluster that lived for 300 million years. There's no process to park it there and then remove it there, and you can't have it do what it does rapidly enough. So I think it's an interesting exercise, but I don't think it's. And then final question was, what will falsify it? When LSST comes online, and if the stuff that I talked about is wrong, right? Like all you need to demonstrate is that, in fact, the stable orbits are not aligned, and the planes are not tilted, and the distribution of Qs is actually peaked at 30. If all of that goes away, the entire thing is just like completely collapses. So that's partially why I'm so excited, is that there is a near-term resolution to this one way or another if we don't detect it right away.
Okay, let's thank Konstantin again.